Hey, when we consider graphs, we're usually talking about the set of all points x and y where the variable y is equal to some function of the variable x. In other words, we're graphing the equation y equals f of x for some function f. When we talk about parametric equations and their associated parametric curves, here the variables x and y are both functions of a third variable, usually called t for time. And let's jump straight into an example. Here we have x equals t plus 1 and y equals t squared. T is an arbitrary independent variable. X and y are both functions of t. And I'd like to come up with a sketch of a graph of this set of parametric equations. And to do that, I'll make myself a chart and just plot points. So I'll pick values for t, compute the values for x and y, plot them on a graph, and see what happens. So here I've started my table. I've picked some values for t between -3 and 3. And you can see from the equations at the top here that when t is equal to -3, x is -3 plus 1, which is -2, and y is -3 squared, which is 9. And similarly, when t is -2, x is -2 plus 1, which is -1, and y is -2 squared, which is 4. And I've filled out the rest of the table in the same manner using the equations x equals t plus 1 and y equals t squared. And setting up a pair of coordinate axes like this, I can now plot these x and y coordinates. And we get these points here. And if you string them together, you get this graph here, which looks at least vaguely parabolic. To be precise, you get a little bit more than this graph here because you don't just get these points, but t is actually increasing from -3 to 3. So there's some direction involved. T starts at -3 here, and we have this point, but then as t increases, this curve goes in this direction like that. So these arrows describe the direction of the parametric curve. Which is to say that a parametric curve is more than just the set of points x and y that satisfy the equations. It also has a direction imposed on it by the values of t as they increase from smaller values to larger values. And that's what's depicted by these blue arrows on this graph. Sometimes it's possible to take a set of parametric equations and eliminate the variable t so that we can rewrite it in the more standard form where y is simply a function of the variable x. For example, in this case, we have that x is equal to t plus 1, and so x minus 1 is equal to t. And since y is equal to t squared, that means that y is equal to x minus 1 squared. And so this is just the usual parabola y equals x squared shifted to the right by 1 unit. In the example that we've been looking at here, we've allowed the parameter t to take any value. It's very common in parametric equations to restrict the values of the variable t. So for example, suppose for this curve, we restricted t to be between -2 and 2. Then our graph would change to just give us this portion of the graph we were looking at before, the portion where t is between -2 and 2. So x is between -1 and 3, etc. Okay, let's consider the parametric equations x equals the cosine of t, y equals the sine of t, as t goes from 0 to 2 pi. And notice what happens if I square both of those equations and then add them. I get that x squared plus y squared is cosine squared t plus sine squared t, or x squared plus y squared is equal to 1. And the graph of this equation is one that we're all very familiar with. It's the unit circle, the circle centered at 0 with radius 1. But in terms of the parametric curve, it's not just that. It also has a direction. We're going around this circle counterclockwise. Suppose instead we had let t go from 0 to 4 pi. Well, we would have the same curve, except now we'd be going around it twice. From 0 to 2 pi, that's once around the curve, but then from 2 pi to 4 pi, that's a second trip around the curve. Let's consider one more variation. Let's look at the graph of x equals the cosine of 3t, y equals the sine of 3t. as t goes from 0 to 2 pi. And we could play the same trick of squaring both equations and adding them, and we get that x squared plus y squared is the cosine squared 3t plus sine squared 3t, which is still 1. And so we're still talking about a graph of the unit circle. It's just that as t goes from 0 to 2 pi, 3t goes from 0 to 6 pi. And so this is the graph of the unit circle, but we're going around the unit circle 3 times. It's the same curve in the way that we're used to looking at curves, but it's not the same parametric curve. It's the unit circle, but it's 3 times around the unit circle. In a moment, we'll get down to some calculus on parametric equations and parametric curves, but first you're entitled to some entertainment. Here we have the pretty impressive parametric curve, x equals the sine of 2t, y equals the cosine of 5t, as t goes from 0 to 2 pi. And then there's this amazing beauty, x equals the cosine of 50t minus the cosine cubed t, y equals the sine of 50t minus sine cubed t, as t once again goes from 0 to 2 pi. You gotta love this one. And just one more, x equals the cosine of 50t minus cosine cubed t, y equals the sine of t minus sine cubed 50t, as once again t goes from 0 to 2 pi. Another beauty. Okay, getting down to business, let's see how we can do some calculus on parametric curves. So suppose we have a set of parametric equations, x is some function of t and y is some other function of t, and suppose we want to consider y as a function of x. Well, since x is g of t, that makes y a function of g of t. And taking the derivative, we get y prime is f prime of g of t times g prime of t by the chain rule. And since y is h of t, y prime is h prime of t. And since g of t is x, f prime of g of t is f prime of x, and that gives us this equation here, which we can solve and get an expression for f prime of x. F prime of x is h prime of t divided by g prime of t. And h prime of t is the derivative of y, and g prime of t is the derivative of x. So what we're really saying here is that the derivative of f, or dy dx, or f prime of x, is dy dt divided by dx dt. I'll say it again, dy dx, dy dt divided by dx dt. You gotta love it. Let's do a quick example. We'll find the equation of the line tangent to the parametric curve x equals t to the fourth plus 1, y equals t cubed plus t, at the point where t is equal to -1. It's very easy to take the derivative. Dy dx is just dy dt, which is 3t squared plus 1, because y is t cubed plus t, divided by dx dt, which is just 4t cubed, since x is t to the fourth plus 1. Plugging in t equals -1 into that expression, we get that dy dx is equal to -1. And so the equation of a tangent line is y equals -x plus b. And all that's left to do is to solve for b. In order to find b, we need to know what values x and y have when t equals -1. And for that, we use these equations here. We simply plug in t equals -1, and we get that x is equal to 2 and y is equal to -2. And we plug them into our equation y equals -x plus b, and we get this result right here, that b is equal to 0. And so the tangent line is simply y equals -x. Let's do one more. We'll find the equation of the line tangent to y equals cosine of pi t and x equals 4t squared minus 2t plus 1 at the point 1, 0. Finding the derivative is once again the easy part. Dy dx is just dy dt over dx dt. You have to be a little bit careful computing dy dt. It's a chain rule problem. And you get negative pi times the sine of pi t all over 8t minus 2. The trickier, the interesting part of this problem is that we were not given a value of t. We were given the point 1, 0. And so what we have to do is try to figure out what value of t gives us x equals 1 and y equals 0. In other words, we need some value of t such that cosine of pi t, which is the y value, is equal to 0, and 4t squared minus 2t plus 1, the x value, is equal to 1. And for what values of t is the cosine of pi times t equal to 0? Well, there are infinitely many solutions to that equation. T is positive or negative a half, positive or negative 3 halves, positive or negative 5 halves, etc. On and on like that forever. On the other hand, solving the equation 4t squared minus 2t plus 1 equals 1, we find that there are only two values of t that make that equation true, t equals 0 and t equals a half. And observe that when t equals 0, cosine of pi t is cosine of 0, which is 1, and in particular not 0. T equals 1/2 is the only value that satisfies both equations at the same time. And so we have that at the point 1, 0, t is equal to a half. And so to find the derivative there, we simply plug t equals 1/2 into our expression for the derivative, and we find that the derivative at that point is negative pi over 2. And so we find that the equation of the tangent line at that point is y equals negative pi over 2x plus b, and all that's left is to find b, which we can do by plugging in the x and y values of the point 1, 0. And when we do that and solve for b, we get that b is equal to pi over 2, and so the equation of the tangent line is y equals negative pi over 2x plus pi over 2. One last point, suppose we're looking at a parametric curve like this and trying to find the equation of a tangent line at 0, 0, or at any of those other points where the curve crosses over itself. Well, clearly there's more than one value of t for which the parametric curve passes through 0, 0, and so you're going to get more than one tangent line at the point 0, 0. So just be aware that that kind of thing can happen with parametric equations. Okay, there is of course a homework up to give you some practice with parametric equations and parametric curves. Hope you enjoy it. See you soon.